One thing about Wednesday, at 1:15 yesterday, I realized I still had a fair amount, or last Wednesday, I still realized I had a fair amount left to cover. And so I went just a few minutes over, and I was really amazed that there was no rustling of paper or anything else until someone pointed out afterwards that class ends at 2:30. So that was a mistake. You got out early on Wednesday. So I do want to finish off the things that we didn't get a chance to talk about on Wednesday. We had talked about redirection, and we'd also talked about fork, but let's just look at redirection for a second. So if we look at this program, so we saw a hello world program before, right? Just prints out hello world, and that goes to standard output, which is connected to the screen. Here, what we're doing is doing the same writing hello world, except we are going ahead and changing what file descriptor 1 refers to. So by default, when we run this program, what will standard output be hooked up to? Okay, so like before I execute any code in it, as I enter the main, where's standard out going? And I'm getting used to this, so let's see. Fabio. To the terminal. Yeah, let's say the terminal. Unless someone in the shell has redirected it, right? In which case it'll be going there. So we don't actually know in this program where it's going, but it's going somewhere. And what we know is we want it to go somewhere else. So we want it to actually go into output.txt. So we're going to create a file called output.txt. And then, what file descriptor does this have? Gary? Yeah, so when I call create, what file descriptor does it, and by the way, why is it create and not create? Anyone? Because way back when, the linkers would go up to 5-character distinction. And so, anyway. So when we start the program, we got 3 file descriptors going, likely. 0, 1, and 2, right? 0 is standard in, 1 is standard out, 2 is standard error. So therefore, when we do a create, it's going to be
3.
I'm actually waiting for Gary. Good question, good answer. Why? I'll tell you, whenever you create a new file descriptor, open and close, it's going to use the lowest unopened or unused file descriptor. So 0, 1, and 2 are used, it's going to use 3. Okay? But we don't want to change the rest of our program, right, our whole one line that did a write 1 hello world. We want to keep this just writing to 1. So how can we get 1 referred to this new file? And that we can use dupe2. So dupe2, how do we find out, David?
Yes.
How do we find out how dupe2 works? Assuming we don't have Google. Or not even how it works, what it does, what its parameters are.
If you know like what library it's coming from,
you could look it up. That's right. You could go look at the header file where dupe2 is, which is probably unistandard.h. And you'd at least see the parameters there and what gets returned. But you actually often want some documentation. The Unix way of doing documentation is man pages. So man dupe2. And that will tell us, okay, so there's a couple things to note here. One, we're providing documentation on multiple related calls. Okay, so dupe and dupe2, and there's a dupe3. Maybe in the future there'll be a, I don't know, dupe4. And so we've got a description. We've got the sort of synopsis of it. Up in the top, it says dupe, and in parens, 2. That 2 up there, it just happens to be like we did a man page on dupe2. That 2, does anyone know what that is? Yeah.
means is in section 2 of the man pages, which is for system calls?
Exactly. There were like 7 originally, I think 7 sections of the man pages, or 8. And the first is user commands, so like ls and cat and so on. 2 is system calls. 3 is standard library calls. So if you look up fprintf, it's going to be in 3 rather than 2. If you want to look up read, that's going to be, unfortunately, where's this one? What section?
1.
It's in 1, which means it's a user command. I'm not sure what the P is. So I really want the system call read, and not this. Uh-oh, how do I do that? Man space 2 space read says I want it from section 2. Does that make sense? Man pages are your friend. You really want to use them.
So does do 2 have a man page because it's a system?
Since it's a system call, it has a man page. And if it were a library as well, it would have a man page. If it were a third-party library, it depends whether they installed man pages for it or not.
Is there another set of slides that I could?
There are, right here. Does anyone else need slides? I'm guessing at least 3 more people do. Anyone? Starts with a G, right? Gabriel. Okay. All right. Okay, so we saw that simple redirect case. Let's now talk about forking. So here we talked about forking, but I don't think we looked at any code on Wednesday. We said that the fork system call, once it returns, you have 2 processes that are almost identical. Their process IDs are different. Their parent process IDs are different. But other than that, they're the same. A duplicate of memory, of registers, everything. And so if it returns 0, fork, then we know it's a child. Otherwise, it has returned the child process ID. So in the child, we're going to run ls. So exec, where would we find documentation for this? Gavin.
Hi.
Oh, okay, Gavin.
Probably section 3, maybe section 2.
It would be section 2, but we don't care because there's no user command fork, so we'll be okay. So, and indeed it is in section 2, because it is one of the important primitives, true?
Sorry, what was the distinction between sections again?
So the sections are what kind of a thing this is. So there are man pages about command utilities, like ls, cat, all those sorts of things, about system calls, about library calls, right? So system calls are part of the kernel, library calls are on top of that. There are on special devices, on file formats, and some other sorts of things too. So those go kind of 4 and on. So let's look again at fork. And so what fork will do is do an ls. But it's doing an ls with an extra process thrown in. And this is what the parent does. It normally waits around. Sometimes it may have something else to do, but it then calls wait. And wait will return when one of its children is finished. What happens if the ls finishes before it's even gotten to the wait? Right, because we get these 2 processes running. I think we were just ending with that, Brad. So what would happen if the exec finishes before the wait gets called? So if the wait gets called first, this is going to wait around until this finishes.
So if that one finishes first, then once the wait's called, it will see that the child process already finished.
Exactly. So this is wait, says wait until a child finishes in the future, or an unweighted child has already finished. Right? If you have 3 children, how many waits do you need to do? 3. Okay? Because if you have an unweighted on finished process, what's another name for that? I mentioned it briefly. Zombie, right? It's a zombie process as well. And there's information in the kernel that has to still wait around for that. Like you can't reuse that process ID ever. Because someone might someday say, what happened to that child anyway? Let's look at execl. Execl is one of a large family of calls, right? Basically of executing a program. So we have a path, right? So this is a complete path. It's not searching through various directories, right? By the time we're getting to execl, we're saying here is where it is. If you want to be supporting multiple paths, multiple directories in a path, you need to check and see, does that file exist? And then we have all the arguments. So whatever arguments we want to pass to the command. You want to have always at least one, which is the 0th argument. And by default, that's the name of the program. So if we are execing /bin/ls, we would run this as ls. Sometimes programs will care about what this 0th parameter is, the command argument 0. A good example would be vim. So vim, you can also execute as ex, runs the same executable, but operates differently. And then the remaining parameters that you might type on the command line. And you have to end with a 0 because this is variable arguments, so we have to know when the arguments end. Right? Printf is variable arguments. How do we know, Jake, when a printf, when we've gotten to the end of our arguments?
How do you know when you've gotten to the end of your arguments on a printf?
Yeah, so, right, because in a printf we can have 2 or 5 or 10 different arguments.
The last one where it goes, I can't remember if the last one is where it goes or not. Like, I can't remember if the last one is a different type.
Let me give you a printf call. Let's say printf. There's a printf call, right?
The format string, you've defined how many you'll have.
Exactly. The format string is how it is knowing how many parameters there are. So somehow the callee has to know how many parameters there are. In the case of execl, it's looking and seeing, I've got a 0 one. So I could just run through them all and I find the 0 and then I stop. If you don't, bad things happen. All right, so we saw this example. Now, let's look at, we saw this example. Let's look at using redirection along with a fork. So, what we're going to do, so in the redirect we saw before, we changed what file descriptor 1 referred to and then ran some code, but it was in our own process, right? Here what we're going to do is change what file descriptor 1 refers to and then run a separate process and show that that separate process gets the new standard output. Okay. So how we would do that? Well, our parent's going to look identical. It's just going to sit and twiddle. Our child is going to, before executing bin_ls, close file descriptor 1, which is standard output, and then create this file. It's going to use the lowest unused file descriptor, which is now 1, because we just closed 1. So now 1 refers to output to this file. The 0600 is the mode, right, that it's using for permissions. So this is, the leading 0 is?
Saying it's an octal.
Octal. 6 is 4 and 2 and 1, so that's read and write for me. The 0 is no read, no write, no execute for others, and this 0 is no read, no write, no execute for a group. So there are, and I think I used it in the previous example, there are constants for these, but it's actually much easier to use this because if you're in the command line and you want to change the mode of a file, you can try and remember the U's and the X's and all that stuff. It's much easier to say, let's say, change mode, I don't know, 644 output.txt, right? Any questions on the fork with redirect? Okay. And this, of course, becomes relevant because your next homework that'll be due a week from today is adding to a shell, which supports things like redirect. Okay, so for a pipeline, let's say we're going to do ls pipe to wc minus l. ls pipe to wc minus l is shortcut for how many files in this directory, right? Ignoring hidden files. So what do we have to do? Well, we know if we want to run the ls, we don't want to run it from the shell, right? Because we want the shell to stick around, and if we exec the ls, it'll be gone. So we know we're going to need to do a fork for the ls, and then we're going to need to do another fork for the wc. So this one is going to be the ls process, and this one's going to be the wc process. Okay? Yeah.
So you said
Right.
1 is standard out. What's 0 again?
Zero standard in, which is always written std, because that's there are constants for these. And 2 is standard error, right? Where the differentiation between standard out and standard error, right, is if you get an error message, you want it to go to standard error, and so that if you're running a program, the normal stuff can get redirected to a file, but you'll still get error messages. So what we want to do is set up these two processes. This is going to be doing an ls. This is going to be doing a wc. We want writes to standard out here appearing as reads to standard in here. Okay. We could use a temporary file, I guess. The shell could do that. It could say, okay, we're going to take bin ls, we're going to spit its output into output.txt, and then we're going to run wc and feed its input from output.txt. Ashley, why is that non-optimal to have an intermediate file?
It's
Slower
slower.
because?
I mean, this just does it directly, but with the intermediary, we'd have to like open and close the file.
Okay, so you'd have to have something in the file system that you're working on and reading and writing. It might still stay cached and not go out to disk, so you might avoid the disk I/O, which would be really intense. Where else could we have a execution savings, a time savings, besides not having to hit the file system?
I'm not sure.
Sarah,
You might not have to call as many system calls
why would we not have to call so many system calls?
because, like, big enough, but
Any other, so, Katie.
what was the question?
So the question is, why would we be better, why is it quicker for ls to be directly outputting into wc than to going via a temporary file, where we run ls, spit its output a temporary file, and then run wc and take its input from there?
You have fewer copies of the data traveling around, so you have to put it in the file first.
Okay, put it in the file and take it up. Here's what I'm thinking. When ls is running, is wc running? No. We have to completely wait for this to run before this runs, assuming that we're writing this to a temporary file. Right? If we're writing this to a temporary file, that means we have to finish writing this before we start doing this. And so we can overlap computation if we run them simultaneously. And if we have multiple processors, then we could just throw each one in a core and go. Does that make sense?
How do you ensure that WC then doesn't read before OS?
That's a good question, and we're going to have to make sure in the operating system to deal with that. So we have to make sure that if WC starts reading and ls hasn't written anything out yet, that this guy does what? Yeah, just blocks. Was there another question?
So if you're using a temporary file, there's no way to make it so that reading will block until some other process is finished writing?
I suppose you might be able to add system calls or something, but in general, no. If I'm reading, when I get to the end of the file, I get it into file, and then I figure I'm done. So, okay. Another thing has to do with the fact that the intermediate data might be very large, like larger than could fit on disk, right? And so I could still have this be generating data incrementally and this be consuming data incrementally and not ever have to actually pay to have it anywhere. That intermediate information.
So you don't have to worry about deleting the file.
And you don't have to worry about deleting the file. Yes. Although, just to let you know, the way, it'll come up at some point. If you want to create a temporary file that you want to use for something like this, some writing, and when you're done, you know you want it to be deleted, what you could do is create it and then remove it. Okay, when you create it, you get an open file descriptor. When you remove it, it's not in the file system anymore, but while you still have an open file descriptor, it's still open. So that's kind of a temporary file that you don't ever have to remember later to delete. Okay? And then once you finally let go of it, it's reference counted and it goes away. All right, so the pipe system call, which of course we would get information about from man pipe, takes an array of 2 ints and some flags. Sorry, an array of 2 ints. Pipe 2 takes some flags, 2 because it has 2 arguments. So it takes an array of 2 ints and creates a pipe, a unidirectional data channel. Okay, so it's going from one to the other. It can be used for interprocess communication, which we have 2 processes and we're communicating between them. And the array returns 2 file descriptors referring to the ends of the pipe. So there's a read end and a write end. Basically, it's like, the black holes with a wormhole, except it's a one-way set of those. So you write into one end, and whatever gets written here appears on the other end. So 0 is the read end, 1 is the write end. Okay, so knowing that, we're going to come back here. So we do a pipe. Why do we do the pipe here and not in the child? Pascal.
What's that question?
So the question is, why do we call the pipe system call here in the shell rather than in one of these 2 children?
Because the pipe, what makes it is read in one direction. And can you go to the documentation again?
Sure. Well, actually, let me just augment with what you were just saying. If we do a pipe here, this process has the read and write end, right? Does this process have anything? No. We want this process to have one end and this process to have the other end. The only way we can have some shared information is if our parent does it for us. So that's why our parent is going to do the pipe. Okay? So the parent's going to do the pipe, the parent's going to do the fork. Does the parent itself care about the pipe? No. So once it's done its forks, it's passed the pipes onto its children, and it can then go ahead and close the pipes. Okay, the file descriptors. And then wait. Which is it waiting for here, LS or WC? Whichever's first. And this is the other one. Okay? In LS, which is the right end, we are closing file descriptor 1, because again, we're redirecting, right? We're closing file descriptor 1, we're closing the read end, and now we have to get the write end to number 1. So we're basically going to dupe 1 into this write end. And go. And then we do the opposite here.
So when you fork, the child inherits all of the file descriptors and whether they're open or closed, but if you, in the parent or the child, change any of that later, that doesn't affect anything
That's
else.
right. So what happens is it gets a copy of that information, and then if any particular process opens and closes file descriptors, that's local only to that process. Okay. But it is shared. If I have, let's say, a read file descriptor shared between a parent and a child, if one of them reads, that's going to update the seek location of the other, if that makes sense. So they're sharing that level of it. But think of it as they have their own array of, because that's all these file descriptors are, just indexes into an array. So they have their own array of what open file is this referring to.
Why is it necessary to close the read file descriptor?
So what's really important is we have to close the write file descriptor here and here. We might be able to get away without closing the read file descriptor. Let me describe what, well, does anyone actually have any guess as to why it's important we close the write file descriptor here and here? Wait. What's your name?
Gavin.
Gavin, right.
Because it's not going to get end of file until everyone closes the right file descriptor.
So WC is going to keep reading until it gets a 0 for read, right? Signifying end of file. How does it know when the file is ended, right? If its input is coming from a file, it knows because the file system knows. But if its input's coming from a pipe, how do we know the pipe is done? We know the pipe is done when it's been closed. So when ls closes that file descriptor for the right end of the pipe, then this guy's gonna, when it does a read that it's end of file. But if anyone else has that right end of the pipe open, any of them could write to it, which means this guy might have more information to read. The only way it knows it's done is if all references to the pipe have been closed. Does that answer your question?
Oh, I was asking for ls. Like, why did ls have to close the read pipe?
So, and I took your question, and I answered a question where I could really tell you why something had to be. So in the read case, I don't think it would hurt. I think we would be fine here. Well, let's just see. So fork. That wasn't it. What is it I'm doing? I'm doing pipe. So if ls doesn't close this, yeah, that's fine. It seems like it'd be messy if you don't, right? Like there's no reason to keep it open. And so therefore, I would say one should. But you don't have to like you do with the right end. Any last questions about this? Okay. Oh, well, that's okay. So we're talking about hardware. We're talking about the x86 instruction set, how GCC calls functions, what the calling conventions are, and just a little bit about emulation. All right, so we got ourselves a PC. The thing to keep in mind about a PC is, right, they've been around for, what, since the early 80s? So 35 years. And so there's a lot of sort of accumulated craft sort of, or expectations that have come along. And so a lot of it is from way back when, that we'll see as we talk about things. Here's an example of a PC board. This is a really old PC board. How can I tell? Yeah, Pentium 130, so is that the late 90s or something? Okay. So let's look at relationship between the CPU, main memory, and input-output. Okay, so we have got several buses that are used for communication between these three entities, where a bus is basically either physically or conceptually, it's a set of wires and some sort of a protocol for communicating, right? So between, let's say, the CPU and main memory, there's a memory bus, there's a PCI bus for going out to cards, the PCI and so on. But all you really have to think of is a bunch of wires and a protocol. And there are lots and lots of different kinds of buses. So here, we're going to have three buses between the CPU, main memory, and I/O. Nindika, what's the address bus used for?
Like if the CPU wants some data, then it sends the address of whatever data
Okay.
it wants over the address bus.
So, thing to note here is this arrow, is a one-way arrow, right? So the CPU is writing to the address bus saying, I want to either read or write data to a particular location. And guess what the location is? The address. Okay. And then on the data bus, Drew?
I'm not sure.
Okay, so let's say we're doing a write. So we say foo equals 3, and foo is stored in main memory. Then on the address bus is going to be the address of foo. On the data bus, we will have 3. Okay? So this shows the data bus that the CPU writes to the data bus. So we wrote to the address bus, we wrote to the data bus. Is that enough? Does our answer, does it now just write? No. Yeah. Yeah, we have to say something like, okay, go ahead. So that's going to be done on the control bus. So we're going to have some information that says, like, I don't know, it's something like it's ready. Okay? And then, who is going to deal with this? In this case, it's memory. We want it to be memory, at least. So we have a ready. Let's even just ignore I/O for a second. So let's say we just had memory. The memory controller would get alerted because of this ready and look and say, oh, I need to read. Where am I reading? Sorry, I need to write. Where am I writing to? The address. What am I writing? The data. And then it'll write. Except, how much data does it write? How many wires are there in the data bus? Yixing?
Data bus. One wire.
More than one. I'd agree with you there. When I write something to memory, how much data am I writing?
One word.
How big is a word?
Every year, I think it's 32.
And that's probably about what these are, 32-bit, let's say. So this would be 32 data lines. And how many address lines?
Each bit is a wire.
Each bit is a wire, yeah. So these are done in parallel. One could have a serial bus, and they're certainly like maybe a universal serial bus. But in this case, going to memory, we do it in parallel. So we have 32 wires roughly for data, or 32 wires for data. And in this case, for the address, if it's a 32-bit machine, let's just say we have 32. Okay, let's just say that for now. So main memory is reading from the address bus, and it is reading from the data bus. Under what circumstance would it write to the data bus? Radon.
Main memory?
Yes, when would main memory write to the data bus?
So if you want to read from memory.
If you want to read from memory, the CPU then is going to put the address. So if we want to say, I don't know, print foo, right? It's going to want to go get the value of foo, and so therefore write the address of foo to the address bus. Does it need to write anything to the data bus? Nope, doesn't write anything to the data bus. There better be some other line here that says I want to read versus write. So there better be some other control here that says I'm reading instead of writing. And then main memory will look and will say, oh, it's ready, and it's a read, so therefore go to my memory, find the data, put it back, and push it out on the data bus. And then presume there's going to be some other thing on the control bus that's going to have to toggle to say, I did it, it's ready, Does that make sense? Okay. There's a little bit, though, that matters. We assumed here that foo was an int. What if instead foo is a char? How many bytes do we want to write if foo's a char? 1. And how many did we want to write if it was an int? 4. So we did 4. So how do we do 1 now? Is the address going to be different? No. Is the data going to be different? No. What's got to be different then? The control has to be different. So we have to have some here thing that says sort of 8, 16, or 32 as to how big it is. Now for I/O, there are two ways that can be done. One way that can be done is the I/O just looks and says, I'm going to handle this address space, and the memory says I'm going to handle this distinct address space. Okay? And that's called memory mapped I/O. We'll talk more about that later. The other possibility is actually having separate instructions. So if you're trying to do I/O, you have different instructions than you do if you're trying to read and write memory. But it actually uses the same buses. So same address bus, same data bus. So how do we distinguish between, let's say, foo equals 3 and output 3, where output is a special instruction that says send something to an I/O port? The address is going to be the same, right? The data? Well, first off, I guess what I want... Yeah, it's not clear the address is the same because we don't even have to provide an address when we're outputting 3. We just put 3 on the data line. But we're going to have some other piece of information here in the control bus that's going to say, is this I/O or memory? Does that make sense? Questions? Gavin? Oh, Gavin. Jake.
Yes. There's a point here where I/O is writing to the address bus, and that confuses me.
That's for DMA.
What is it for?
Direct memory access, if the I/O wants to be able to access memory.
So I'll give you an example. It can happen. Yeah, I/O can write to memory. So I can set up a SATA drive controller, and I can say, SATA controller, I want you to read 1024 bytes and put it at this address in memory. And please do not get me involved. So therefore, the I/O has to be writing to the bus that the memory is going to be reading. All right. We have a stored program computer. I mean, what else would it be? Because the memory has instructions and it has data. There are computers, or there were computers, without a stored program. So you can think of these as, let's say, hardwired computers, where we might have, wired up connections that connect it up, so that the instructions are not stored in main memory, like the data. But we just go through fetch an instruction, execute instruction, fetch instruction, execute instruction, and so on. And when we are fetching those instructions from memory, and we're also reading and writing to memory. And usually, we don't overlap the two, right? Commonly, we don't, let's say, modify our instruction stream as we're going. Could one do that? Sure. All right, so here in the x86, thank you, David.
Wouldn't ASIC qualify as like
Sure, an ASIC would be, let's say, some sort of computation engine that has data but no stored program. So we've got an instruction pointer. Instruction pointer IP. Instruction pointer. But we are EIP. E, I think, stands for extended. We're going to be using E's for a lot of things, and this has, again, part to do with the history. So we've got an instruction pointer that points to, that is, holds the address of the next instruction to execute. And then it fetches that instruction, and then executes the instruction, updates the EIP. So you don't explicitly change the EIP, unlike other registers. You implicitly change it. So by executing the instruction changes it, doing a jump call changes it, doing a call, doing a return, calling an interrupt, all those things will change the instruction pointer. How much does the instruction pointer move from instruction to instruction? Dave?
Depends on the computer, but
Okay, let's say x86.
it would be like 4 bits 8 bytes. I mean, it would jump. It would jump 8.
It depends.
Else.
It depends how long the instruction is. That's how much it'll jump. So we'll see there's some craziness that's in there too. You can take an instruction and then you can add a prefix. Or you can, actually there are multiple prefixes that you can add that are all valid and change how the instruction gets interpreted.
What's the longest instruction?
Yeah, I don't know. But that's a good thing to look up.
How long?
You might be able to validly add an unlimited number of prefixes. So here are the registers one has, okay, the basic registers. So these are broken down, again, because of history. So originally, the IBM PC was an 8086, which was a 16-bit machine. So its register sizes were 16 bits. And so the 16-bit registers were called AX, BX, CX, and DX. And you sometimes might want to get the top 8 bits or the bottom 8 bits. And so you can actually use AH and AL, BH and BL, CH and CL, DH and DL. It's the same register, it's just pulling out different part of it. This got extended so that now we have EAX, EBX, ACX, and EDX, which are the 32-bit equivalents. Can you still use AX? Yes, it'll refer to the bottom 16 bits of the EAX register. And similarly for AH and AL, they'll work. We have the EIP, but I don't call that it's not a general purpose register because you can't go and change it explicitly. Here, you can read and write from any of these registers. Okay. SP, stack pointer. BP, not sure why we get the B, but this is the frame pointer.
Base pointer?
Okay, base is I can see where you get that then. So we'll talk some more about that. But basically it provides us a chain of stack frames showing basically the call stack. So that one can go and look at, let's say, the parameters of the procedure that called you, or the local variables of the procedure that called you. Never used in C, but certainly used in some languages. And then there also are some miscellaneous registers. I think it's EFG. But we're not going to be using too much here, but they can be used. They weren't there in the original 886. Okay. So normally you're just dealing with sort of A, B, C, and D. And add EX10 basically says EX equals EX plus 10. There's a flags register. So the flags register has a bunch of information. So let's see, carry flag, sign flag, zero flag, all are very useful when you are wanting to do branching. So you want to test if A is less than B. How would you do that? You could have a test instruction that tests one register against a constant or one register against another register, and then looking at the values of these, which you don't usually explicitly do, although you could, you can tell what was the situation. Was the first thing less than the second thing, equal to the second thing, greater than the second thing? If I did an addition, did I get an overflow, which would mean the carry flag was on, for example. All right, so we have these registers, and that's great. We need also a way to deal with memory. And so let's say here. So we are moving, and I'm going to say this syntax here is AT&T syntax. Okay? There is another syntax that you will also see, which is slightly different. They don't say move L, they just say move. They, I believe, don't use percent signs, but the most important thing about the other syntax is that the source and destination are swapped. I'm sorry. You're going to mostly be using this, but if you look at Intel documentation, you'll see they're reversed. Okay? And you will have to look at Intel documentation. So I can move one register to another. So that basically is just saying one register equals another register. I can move a constant into a register. So here I'm moving how many bytes?
4.
4, which you can't tell by looking at that constant. You have to look actually at here. That's long. So you could move B, move W, or move L. And notice the distinction between the $ and the non-$ version of this. So the $ says immediate. That is, it's just a constant. Whereas, if you don't have the $, that says whatever is at address 123. Okay, so it's basically taking the address 123, treating it as a pointer. It's an int32 pointer because this is a long. That goes with this. And we're dereferencing it. Okay. So, in the immediate case, are we going to main memory?
No.
There's no main memory. No. We are getting the value from our instruction itself. Right? It's embedded in the instruction. And so in that sense, if the instruction came from memory, that's coming from memory. But this itself doesn't generate another. Register mode, is there any access to main memory? No. There is indirect. Okay? And then we can also do indirect through a register. Okay? So it's very similar to the indirect case, or sorry, to the direct case, where we're going via constant. But this is going via a register. And then finally, we can have a displaced version indirect. So it's sort of like if you have a struct and a pointer to a struct, it's like offsetting a field within there. So you can say indirect, but add, before you do the indirection, add so many bytes. And most instructions can take a memory address. So what if I want to move something from address 1234 to address 5678, Julius?
What's the question?
So I want to move something from address 1234 to address 5678. I want to do the equivalent of this. Let's see, star in 32T star 5678 equals star in 32 star 1234. Okay, so read from 1234, write it into 5678.
So you store, you do, but you store in register.
Yeah, you've got to store in register because you can't provide two addresses in the same instruction. So you've got to move 1234 into a register. What would you use there? Which mode? Immediate, direct, indirect, displaced. Yeah, direct, exactly. And then you'd also use direct mode to write that register back out. Okay. And of course, you've blown away whatever in that register, so you better have saved it beforehand. Does that make sense? So there are a few weird instructions that take more than one memory address, and I'm not going to get into those. They're not used very often. We've got stack memory. So the stack is see how I would describe it. So since there are some instructions that deal with the stack, it is actually part of the architecture. But a lot about the stack is convention. So much of the stack and its usage is convention. Okay? That is, you wouldn't have to use. In fact, you could go away completely without using any of these special instructions that deal with the stack. Yes, so almost completely. I'm thinking of one exception, but I'll show it to you in a moment. So we can, for instance, push L The L says it's a long, right? And we're pushing the EAX register. So that pushes it onto the stack. The stack grows down. Right? So let's say this is the old information on the stack, and this is the newest information on the stack. This is a bad way to show this, so hold on a second. Okay, when I say the stack goes down, I don't mean in whatever pictures I do. What I mean is it goes down in memory. Okay, so if this is memory address 5678, and this is memory address 5600, and this is my stack, where's the newest thing on the stack? It's at the top, right? The top of stack. So this is the newest, and this is the oldest. The stack pointer would be pointing here. The newest. So when I push EAX, that's basically going to decrement the stack pointer, making room for this new thing I want to push, and then it will move that register I want onto the stack. Does that one make sense? All right. Popping does the opposite. If you make a call, that is, you make a procedure call, that had the effect of these two non-existent instructions. Push the instruction pointer. Why is that non-existent? Because you can't push the instruction pointer. There's a limited number of things you can do with the instruction pointer, that's not one of them. But effectively, that's what's happening. It's pushing that, and then it's changing the instruction pointer to this new value. Again, you can't directly do that. You could do a branch, which would have the same effect. And in return, pops from the stack into the instruction pointer. Does that make sense? Questions? Okay. So more memory. Let's go back to 886. So we're back in the early 80s. All right. We have 16-bit registers. Okay. So for instance, stack pointer. It's not ESP because there hasn't gone on to 32 bits back then. So this is 16 bits. We've got, let's say, I don't know, the AX register is 16 bits. And yet we have a 20-bit address bus. So that seems like 4 bits that are wasted. But if I go back here and I look at one of these instructions, if I do a move to a particular, let's say using direct accessing, so I want to go change a memory location, I can use a register that's limited to 16 bits to specify the address. And yet there's 20 bits of address space on the bus. So what's going on? Well, what's going on is segmentation, which was why I didn't use the 8086 in the early 80s. I used the 68000, which had a flat address space and didn't have these complications. So here's what happens. When you reference an address, it gets manipulated before it gets put onto the address bus. So what happens is we take our virtual address, which is this 16-bit address, and that's a virtual address, and we add to it a segment value times 16. Which segment? The seg depends on which register. But the fact is, so we're adding this segment register. So these are 16-bit values. Okay? So if I add a 16-bit and 16-bit value, I get at most 17-bit value, right? So that at least tells us how we have 17 addresses. Question, Kevin?
Which segment is used for direct addressing mode?
It depends. So I'll show you in just a second. The multiplying here by 16 basically gives us another 4 bits that we can move. So that allows us to straddle all of the 2 to the 20th addressable memory locations. The code segment is used for EIP. So yeah, and remind me your name.
Ryan.
Ryan, okay.
Do modern machines with 32 and 64-bit process still uses?
So the machines do, because it's there. Do the operating systems is really the question. And the answer is almost completely no, because it's so much easier to have just flat address space. At the time, this made a lot of sense, right? Because your instructions can be smaller if you're only dealing with 16-bit values, right? So your actual code is smaller, and your pointers are smaller because they're 16 bits, and there was not a lot of memory around, really. So it did make some sense. But I'll tell you, when you're using C, it's really complicated, because if you want to take the address of something on the stack, you can't just use the stack pointer as its value, because really it's the stack pointer plus the stack segment register. And that's different from a value in main memory, where it's its address plus you have to deal with the data segment. And so you had weird things that you had to do in C to make that happen. And you had to know which kind of thing it was.
Sorry, can you explain again why you're multiplying the value in data segment by 16?
So the reason we're multiplying by 16 is we've got our 2 to the 20th space here, right? So this is 0 to 2 to the 20th. And if we just use a virtual address, that takes us from 0 to 2 to the 16th, right? If we just added in the value of the segment, which is also a 16-bit value, the highest we could get would be up to 2 to the 17, right? If we had a very large number for the segment, and then we added in. So basically, what the segment register is doing is saying, you get to move your entire 2 to the 16th window almost wherever you want in this range. It has to be on a 16-byte boundary. So you can move it to be up to the top, right? So basically we're moving this up to here. And if so, the segment register would be this value, right? Does that make sense? One thing we is it possible now to have overlapping segments? Yes, and that turns out to sometimes be useful. You had a question?
So I guess I'm kind of confused. So is there, are the segment registers just constants, and then you just pick one of them, or do you go in and
You can change them programmatically. You can change them programmatically. So if you had, way back when here, so let's say you have, I don't know, some giant program that has 200K of code, okay? Well, it's not going to fit in one segment, because one segment can hold 64K. So you'd have to break your program, which is not easy, apart into multiple segments, and then when you called from one segment to another, someone would be having to change the segment register. Segment? Okay. Other questions? Okay. So code, stack, and data were the three main segment registers. There's the string operations, which are weird and not used very much, which have their own segment register.
What was the reason for the limitation on segment size to 256K? Oh, that's for the that's just because of the addressing.
Oh, the 2 to the 20th. I don't know where we're getting 256K. So tell me. Oh, where's 256K coming from?
Oh, I thought that was what you said.
Oh, I just said if you had a giant program like 200K.
Okay.
So. All right. So how much memory did could the original 8086s support? Ishan.
16 bits.
No, they can actually support more than 16 bits of memory because the memory is communicating with the address bus, right? And so the address bus is how large?
20 bits.
20 bits, which is yes. So, right, always remember 2 to the 10th is approximately 10 cubed, right? 2 to the 10th is a K. And so you can go from there. So they could support a megabyte, although they didn't have a megabyte of memory to begin with. So my first 4 megabytes of memory cost how much? Any guesses? $1,600. So, and my 10 megabyte hard drive was $800. So, the good old days. So at 8386, which was several series later, adds 32-bit data and address buses. In the early 2000s, x86-64 has 64-bit data and address buses. We have this backward compatibility issue. The backwards compatibility issue is when we boot, we might be booting software that doesn't know how to, that doesn't understand 8386 or 8286. It's some code that was written for an 8086, and we somehow think it's still important to run it. Okay? So because of that, we boot in 16-bit mode. We boot as if we're an 8086. And then we have to do some machinery if we want to enable, meaning more than that. So we boot in 16-bit mode, which is called real mode. Do we have segments in real mode? Yes, because what I told you about was x886. Do we have EA, the extended versions of the registers? EAX, EBX, no, we have AX, AHAL.
So when we boot into real mode because of old software?
Because we used to boot in real mode, and let's say someone changed to not using real mode. Okay? I've got my Linux distribution. Today, it boots in real mode, right? It assumes it's real mode because it was in real mode way back when. If now I've got a machine that doesn't boot in real mode, what do I do with my Linux? I have to have 2 different distributions of it or something, 2 different versions, one of which knows to boot in real mode and one of which knows to boot in non-real mode. So because we started that way, there's no easy place there is to have changed that. But it's all historical, and we wouldn't do it this way if we were starting from scratch. So we boot in 16-bit mode. And as we're running, we're operating in 16-bit mode. So when we were dealing with instructions, they're 16-bit instructions. And this is the, both XV6 and JOS have to deal with this. So we switched to protected mode with 32-bit addresses. Okay? So, for instance, the instruction pointer, once we switch to protected mode, is now a 32-bit value rather than just a 16-bit value. There are, so here's an example. So this prefix basically gives you, on an instruction by instruction basis, you can say, for this instruction, I know I'm in 16-bit mode, but I would like to operate on a 32-bit value. So please treat this as a 32-bit version.
So when you switch into 32-bit mode, how does it determine the top part of the 16-bit registers?
It's actually still there.
So how do you know, so what happens with the instruction pointer? Like if it goes to the next instruction, but you don't know what the top bit of the instruction pointer is?
So the way you would be getting into 32-bit mode, right, you would jump or in a 32-bit address. You would provide a 32-bit address.
That makes sense.
And your jump would have to say jump with a prefix because I want to give you a 32-bit address. Okay, so the prefix, actually this is a little bit of a lie. Prefix x66 doesn't give you 32-bit addresses. It gives you 32-bit addresses if you were in 16-bit mode. Guess what happens if you're in 16-bit mode? Sorry, in 32-bit mode. It trips, exactly. So it's a toggle as opposed to a setting. So you will see, if we look, for instance, so in XV6, if you look at boot.s, which is the assembly language code, you'll see there is an assembler directive that says insert the 66, basically. I want you to start putting 66 in these instructions. Okay? Because it's not particularly easy to specify that in the inline assembler. All right. The 8386, as well as having these 32-bit data, 32-bit addresses, also adds virtual memory addresses. So we actually have page tables which refer to various pages in memory, so that you can have what appears to be a contiguous memory space that's actually composed physically of this contiguous memory. And you can have holes and stuff like that, and we'll talk all about paging. But 8386 adds that. All right, we can also do I/O. So here's an example where you are printing to the line printer. Okay, so we will read a byte from the status port. So there are 1,000 or 1024 ports, and you can read and write to any port. And depending on what port you read and write to, there's particular hardware at the other end that is dealing with that. So here we wait until the line printer is not busy, and then we output one, in this case, integer, and then we tell the line printer, hey, we just put something there, so we're going to do a strobe and a 0, which says to you, go ahead, and I just wrote something there, deal with it. So in B and out B map to particular instructions. So these will map to I/O instructions. Okay. There are only 1024 addresses, and you have to use a special instruction. So there are a bunch of legacy devices that still use the input-output space, but most devices use memory mapped I/O. So they'll just take a part of the address space memory, and you'll use that for reading writing data.
How do different devices negotiate what part of the address space they're taking?
It depends. NuBus, which was used by the Macs way back when, said when you put in an expansion card, which slot you went in controlled which address space you were, and the device could figure out which slot it was in, so it knew which address it was in.
But how does the driver know which slot the device is supposed to be working with? Is in?
The driver would iterate through the devices and go look and see what they were. Another possibility, used to happen a lot for PCs, was you had to set a toggle on the card to say where its address space was. And so you can imagine how hard that is for, telling your parents, hey, you got a new card, you got to make sure it doesn't conflict with the existing card to make sure your driver knows what you set it to. Yeah. These days, we actually have software that runs at boot time for devices to sort of negotiate and get information, which is written, I think, in Forth, I believe is that. Anyway, so we use normal addresses instead of these special instructions, and it works like magic memory. So it, by the way, is not accused. Okay? It is accessed, like normal memory. So yeah, if you want to accuse it, you have to do it totally differently. It doesn't behave like real memory, though, right? Because there's no actual memory there. When you read and write, there can be side effects. When you read and you read again a little later, it may be different. So this does mean your language may need to know. So for example, let's say you're reading from a status byte and you want to say while star status is not equal 3. Okay? And here, you know, status equals, you know, OX1234. So it's some pointer, right, to an actual address in memory, but it's not really a memory address. Okay. And actually, let's even just say this. Star status equals 1. And then we keep going while status equals 3. If you've got a nice, smart compiler, what does it do with this whole while loop? You get rid of it. It's 1. I know it's not 3. I can prove it at compile time. We're done. Not very good for memory map. So how would we change this in C to tell it not to do that? Actually, Jonathan. So how do we tell C, hey, read this even if you think you don't need to? It's a designation that says this could change out from under you. Volatile. So, and you have to get it at the right location within the pointer to specify it's not that status's address will be changing, but it's the value it points to will be changing. So volatile is necessary to turn off a lot of optimizations. So when we're doing operating systems, this can matter, because if you're writing a device driver, then you may definitely need to be hitting memory mapped values that can be changing out from, you know, from under a compiler, so to speak. Questions on memory mapped I/O? Okay, the physical memory. We've got an address space, a 32-bit address space. And so, because of history, especially, there are special requirements for various parts of the memory. So the VGA display is here. Right, so we have, what's 128K of VGA memory, where VGA is, right, the 640 by 480. That's good. Low memory is from 0 to 640. So way back when, 640K was what you could easily deal with. Above 768, we have some devices. We have the BIOS up here at 960, and then extended memory started at 1 meg. So you have this non-contiguous memory space from 0 to 640K, and then from 1 meg up. All right. The memory map devices go up here. Let's see what else happens. If you do a power on, then that starts, it jumps to the ROM at, what is it, OX, FF, F0. So basically, the very top of the ROM is where it will start executing. So you have to have something there which contains instructions. So this is not the most convenient layout of memory, and so we will be using our paging hardware to rearrange this so that we have a nicer looking architecture, or nicer looking address space for our kernel, and nicer looking address space for our user programs. Bunches of instructions, we've seen some of them already. Move, moves data between registers or between register and memory. Push and pop, write via the stack pointer and update the stack pointer. You have arithmetic, like testing, to see whether one value is bigger than another, or really what the relationship between one value and another is. Shift left, shift right, so the things kind of that correspond to the C operations. You can even add and subtract. These are the I/O calls, so those deal with those 1024 I/O ports. You can call a subroutine, return from a subroutine, jump to a particular value, that is, just branch there, or jump if it's 0. If what 0? If the last thing you operated on, if the last thing you tested, or the last thing you moved is 0, then that'll be 0. Again, it's looking at those status flags.
why do we start at that very high address at boot time?
So
I would have assumed we would start at the bottom of the last rung or something.
I will have to look into that because it seems like, yes, we've been saying two different things. So how could it... yeah, rather than conjecture, I will tell you on Wednesday. Interrupts and interrupt returns, we talked about briefly last week, right? This is the way we're going to actually be calling into the kernel. So if you're in user mode and you do an interrupt, then we call it trap, then it will enter kernel mode via a well-known set of entry points and switch into kernel mode. I mentioned this confusion between Intel and AT&T. All right, so that's it for today. We will talk about calling conventions and emulation later. The calling conventions are going to be useful, unfortunately, for doing homework 1. But I'm in the lab and we can talk about it. So I will be in the lab much of the afternoon, and I will for sure be there to 9, which is when I hope all of you can be there as well. Right? And I'd suggest, yeah, working on homework 1 and working on lab 1, and it'll probably be much easier than just working by yourself.